So, let us recall what we have stated about Taylor series method. The Taylor series method has the desirable property of high order local truncation error, but it also has some disadvantages, namely it requires computation and evaluation of the derivatives of f of x comma y, and it is a complicated time consuming procedure for most problems when f of x comma y is complicated, and it is too expensive for most practical problems, and it is very seldom used in practice because of the computational effort which are required to carry out the details. So, as I said earlier, this leads us to look for other single step methods which imitate Taylor series method without the necessity of computing higher order derivatives. Such methods are Rungakutta methods. They mimic the Taylor series method. Let us see how, and then derive Rungakutta methods of different orders. The derivation requires the knowledge of Taylor's theorem in two variables. So, let us quickly go through this result, namely Taylor's theorem for a function of two variable, which says that suppose f of x comma y and all its partial derivatives of order less than or equal to n plus 1 are continuous on a rectangle R, which consists of points x comma y with x lying between a and b and y between c and d, and if x naught y naught is in D, then for every x y in D there exists a psi between x and x naught and mu between y and y naught, with f of x comma y equal to Pn of x comma y plus Rn of x comma y, where Pn of x comma y is f of x naught y naught plus x minus x naught into partial derivative of f with respect to x evaluated at x naught y naught plus y minus y naught into partial derivative of f with respect to y at x naught y naught plus the higher order terms plus etc. plus the term involving the nth order partial derivative that constitutes Pn of x y, and Rn of x y is the rest of the terms, which is given by 1 by n plus 1 factorial sigma j equal to 0 to n plus 1 Cj x minus x naught power n plus 1 minus j into y minus y naught power j into n plus 1th derivative of f with respect to x n plus 1 minus j times with respect to y j times evaluated at psi comma mu. This Rn is called the remainder term associated with Pn, and Pn of xy is the nth Taylor polynomial in two variables for the function f about x naught y naught. This is not something new to you. You have already learnt it when you have discussed function of two variables in your calculus course. So, let us just recall it in the same notation in which you would have learnt. So, let us look at the board and write down the details. So, if I have a function of two variables and I give a small increment h to the first argument and an increment k to the second argument, then using Taylor series it is given by f of x comma y plus the increment in the first argument, that is h, multiplied by the partial derivative of f with respect to the first variable for which h is the increment, plus increment in the second argument which is k into partial derivative of f with respect to the second variable y for which k is the increment. So, this is set of terms which involve first order partial derivatives. Now we go to the next term, which is 1 by 2 factorial into h square into the second order derivative of f with respect to x plus 2hk into the second order derivative of f with respect to x with respect to y, which is a mixed partial derivative, plus k square into second order derivative with respect to y twice. Let us write down the third term, which is 1 by 3 factorial h cubed into the third derivative of f with respect to x plus 3 h square k into third derivative of f with respect to x twice and y once plus 3 h k square into third derivative of f with respect to x once and y twice, and then k cubed into the third derivative of f with respect to y thrice, and so on. So, if I move on up to 1 by n factorial into the terms, that is what I call as Pn of x comma y. To this I should add Rn of x comma y, which will be the first neglected term after this, which will involve 1 by n plus 1 factorial into the terms which involve derivatives of f, which are partial derivatives of f of order n plus 1 with respect to x with respect to y suitably. This is what we have written there. How? We want f of x comma y. We want to expand about the point x naught comma y naught. So, I rewrite this as x minus x naught plus x naught comma y minus y naught plus y naught. So, I want to expand about x naught y naught. So, my increment is x minus x naught to the first variable and y minus y naught to the second variable. So, it is f of x naught comma y naught plus the increment given to the first variable is x minus x naught into partial derivative of f with respect to x, increment given to the second variable into partial derivative of f with respect to y. So, these are the first set of terms involving first order partial derivatives. What will be the next term? 1 by 2 factorial into h square, which correspond to square of x minus x naught into f with respect to x twice plus 2 h, which is x minus x naught, k, which is y minus y naught into second order derivative with respect to x with respect to y once, right, and then y minus y naught the whole square into f second order derivative with respect to y twice. That will constitute the terms involving second order derivatives and so on. And now I have the term involving 1 by n factorial. All these terms constitute Pn of x comma y, which is called the nth polynomial, Taylor polynomial in two variables for the function f about the point x naught y naught, and to this I should add Rn of x comma y, which is the remainder, and this will involve 1 by n plus 1 factorial and terms involving the n plus 1th derivative of f with respect to x with respect to y appropriately. So, this is a Taylor expansion for a function of two variables about a point x naught comma y naught. So, we will make use of this in deriving Rungakutta methods of appropriate orders. So, let us now move on to the derivation of this method. So, first of all we shall derive Rungakutta method of order 2. So, I will explain why we call this as a method of order 2 later on when we complete our derivation. It is an explicit method. The reason is that if we know the values of y at x1, say y1, then we can march one step ahead which is at a distance of h units from x1, namely I can go to the point x2 and compute y at x2, namely y2 explicitly with the knowledge of with the knowledge that I have about the function y or f of x comma y at the point x1, and go ahead like this and determine the solution at each of these points explicitly, and so it is referred to as an explicit method. So, in Rungakutta method of order 2, what is it that we are interested in? So, let us just look at the board to see what we want. So, we would like to derive RK method, we call it as RK method, Rungakutta method of order 2, and in this method we solve a first order differential equation of the form dy by dx is equal to f of x comma y with y of x naught equal to y naught, and go up to the computation of our solution at xn. So, we have an interval x naught to xn, which we divide into number of sub intervals of the form x naught to x1, x1 to x2, etc., such that xi is x naught plus ih for I is equal to 0, 1, 2, 3 up to n. So, at the first step we would like to compute y at x1. This is approximated by y1. So, y1 approximates y of x1, and I would like to derive this method in such a way that y at x1 is going to be y naught plus some constant c1 times k1 plus c2 times k2, where c1 and c2 are constants to be determined, and k1 and k2 are functions such that k1 is h into f of x naught comma y naught, and k2 is h into f of x naught plus alpha h y naught plus beta into k1. So, you observe that k1 involves evaluation of the function f which appears here at x naught y naught, and we know both x naught and y naught. So, immediately this can be obtained. And what is k2? That again involves evaluation of the same function, but now at a point x naught plus alpha h comma y naught plus beta k1, where again alpha and beta are constants to be determined. And where does this point, where does this x naught plus alpha h lie? We are computing the solution at x1, namely y1. So, I want this point x naught plus alpha h to be a point between x naught and x1. So, it is immediately clear that alpha is less than or equal to 1. This point can be x1 also when alpha is 1. So, I want the point to be somewhere between x naught and x1. Already I have taken the function value at x naught y naught. So, I would like to evaluate this function at some point x naught plus alpha h. I do not know what this alpha is now, I have to determine. Not only alpha, I also have to determine the constant beta. So, we now have 4 constants C1, C2, alpha, beta, with the restriction that alpha must be less than or equal to 1, such that these 4 constants have to be evaluated. What is the condition with the help of which you are going to determine these constants? The condition is that the method that we have written, so I call this as star, right? This method star agrees with Taylor series method, of order as high as possible, as high as possible. remember, Taylor series method involves derivatives of certain functions, but I can replace the derivatives in terms of the partial derivatives of f of different orders. On the other hand, this method involves only the function evaluations at certain points in the interval x0 to x1 when you want your solution at x1, knowing your solution at x0. So, the requirement is that the constant C1, C2, alpha, beta must be determined in such a way that method star mimics or it agrees with the Taylor series method of order as high as possible. So, let us obtain what this star is and what is Taylor series method of order as high as possible that matches with this method star, and then determine the constants C1, C2, alpha and beta. So, let us first take K2. So, what is K2? K2 is h into f of x0 plus alpha h, comma y0 plus beta into K1. So, I have a function of two variables and each variable is such that some increment is given to the first argument, the increment is given to the second argument. So, I use Taylor's theorem for two variables and write this as f of x0 comma y0 plus alpha h into partial derivative of f with respect to x plus beta k1 into partial derivative of f with respect to y. Then I take alpha h the whole square by factorial 2 into f with respect to x twice. Then 2hk if the increments were h and k divided by factorial 2. So, I simply have increment alpha h multiplied by increment beta k1 into partial derivative of f with respect to x with respect to y. And then the next term will be square of the increment given to the second variable. What is the square of the increment given to the second variable? It is beta k1. So, beta k1 the whole square divided by factorial 2 into f y y. That is the next term. So, these constitute terms involving the second order derivatives plus terms of order of h cubed, h square k and then hk square and k cubed. In case we require them, we will write down. Let us see what happens as our computations are carried out. So, remember that terms on the right hand side, all these have to be evaluated at the point x0, y0. So, let us simplify this further. So, h into f of x0, y0, I shall simply write it as f, remembering that it should be evaluated at x0, y0. Then the next term plus alpha h into fx plus beta, what is k1? I already have k1 as h into f. So, I substitute k1 is h into f multiplied by fy, and then I write down the next set of terms which give me alpha square h square by factorial 2 fxx plus alpha beta h into what is k1? hf. So, that will give me h square f into fxy plus beta square k1 square is h square into f square into fyy divided by 2 plus order of terms involving h cubed, h square k, hk square, k cubed and so on. So, this is what we get for K2. So, I shall substitute in this method. So, we have therefore y1 to be given by y0 plus C1 into K1 is h into f plus C2 into K2, and K2 has been computed. So, K2 is h into f plus alpha h fx plus beta h f fy plus the terms alpha square h square by factorial 2 fxx plus alpha beta h square f fxy plus beta square h square by 2 f square fyy plus order of these terms, that is h that is k2. So, which again can be simplified and written as y naught plus h into f into c1 plus c2. So, we have these two terms. Then the next term is h square into alpha c2 into fx. Then the next term h square into beta c2 into fy. Then I observe that the terms are c2 into, I have h square appearing in all the three terms and a h outside. So, I shall take c2 into h cubed multiplied by, write down the rest of the terms, alpha square by 2 fxx plus alpha beta fxy plus beta square by 2 into f square fyy. That is the next set of terms. And then I have terms now of what? Already I have h cubed, h square, k, etc. That must be multiplied by h. So, they will be all be of the order of h power 4, h cubed k, h square k square and h k cubed. So, such terms will appear. So, this is what our method is when we use Taylor expansion for a function of two variables. What is it that we want? We want this method to agree up to Taylor series expansion up to order as high as possible. So, let us write down the Taylor expansion. Namely, I want to compute what is y of x1. It is y of x naught plus h, because y1 approximates y of x1. So, I would like to get a Taylor expansion of y about the point x naught. So, it is y of x naught plus h, which is x1. That will be equal to y at x naught plus h into y dashed at x naught plus h square by factorial 2 into y double dashed at x naught plus h cubed by factorial 3 into y triple dashed at x naught plus etc. This is Taylor series. So, we shall now substitute for these derivatives and write down the solution. So, we now write down what y of x1 is. So, y of x1 will be equal to y naught plus h into y dashed. We know the differential equation is y dashed is equal to f of x comma y, and the initial condition is y of x naught is y naught, and we want y dashed at x naught. So, it is f evaluated at x naught y naught. Then the next term h square by factorial 2. What do I have? Y double prime. When y prime is f of x comma y, y double prime is d by dx of f of x comma y. F of x comma y is a function of two variables x and y. Y itself is a function of x. So, it will be f with respect to x partially, f with respect to the second argument y into y with respect to x, which will be y prime, and that y prime is f. So, I know y double prime now, and I have to evaluate it at x naught. So, the next term will be h square by factorial 2 into y double prime at x naught. So, it is fx at x naught y naught plus ffy at x naught y naught. Now, let us go to the next term. So, I have h cube by factorial 3 into, I require the third derivative, namely y triple prime. So, we already have computed this third derivative in the previous class. Let us work out the details. So, I need to get d by dx of this. The term is a function of x and y, and I require the derivative d by dx of this. So, it is going to be the partial derivative of this with respect to x plus this with respect to y into y with respect to x. Now, I apply the product rule, right. Then partial derivative of f with respect to x, f with respect to y into y with respect to x. Then the next term f into partial derivative of fy with respect to x plus partial derivative of fy with respect to y into y prime, that is f. So, this will give you the third derivative. So, we shall substitute there. So, I have fxx, then I have f into fxy and f into fyx, f being continuous, the mixed partial derivatives are equal. So, I can combine this and write it as 2f into fxy. Then I have f square into fyy. So, let me write down that also. And now, we are left with the terms fx into fy, which comes from here, then f into fy square, which comes from here. So, we have taken into account all the terms. So, plus order of h to the power of 4. So, we have written down Taylor expansion about the point x naught in terms of the partial derivatives of f, and all these terms on the right hand side will have to be evaluated at x naught, y naught. Similarly, all the terms which appear in the method star which we have developed also have to be evaluated at x naught, y naught. We now impose this condition. The method that we have derived here must match with Taylor series method, which is written here, up to order as high as possible. What is the maximum order of the Taylor series method with which the given method star which we are deriving will match? So, let us look at the first term in y1 here, that is y naught. In the Taylor expansion, it is y naught. So, that is matched. Move on to the next term. I have a h f into C1 plus C2 in the method that we are deriving, and here we have a h into f. So, in order that these two match, we must have C1 plus C2 to be equal to 1. If C1 plus C2 is equal to 1, then the term here is the same as the term in Taylor expansion. Fine. We move on to the next term. So, we take the coefficient of fx here, which is h square alpha C2, and we observe the corresponding term in the Taylor expansion. We have h square by 2 into fx. So, if we equate the coefficient of h square fx from both, we get half to be equal to alpha into C1, alpha into C2. So, alpha C2 must be equal to half. Then we take the next term fy into h square. The coefficient is beta C2, and I have fy h square, and its coefficient is equal to half. So, we have matched the coefficient of h square terms in both the methods. We now move on to the coefficient of h cubed term. We observe that we have a fxx term here as well as here, f into fxy term which appears in both of them, f square fyy, that again appears in this term. These coefficients involve C2 in it, right. I can take the corresponding terms fxx whose coefficient will be alpha square by 2 into C2 and equate it to the corresponding coefficient here, which is 1 by 3 factorial. I can do it for each of these terms, but I observe that I have 2 extra terms, all right, which I cannot match with the Taylor, with the method that I have, because my method does not have that term in it. One may say that if I choose my C2 to be equal to 0, these terms do not appear at all, but I cannot make this C2 to be 0, right. In that case, what will happen when C2 is 0? Then we get inconsistent values here. Alpha into 0 will be half, beta into 0 will be half. So, C2 cannot be made 0, that is clear. So, C2 has to take a non-zero value. So, when C2 takes a non-zero value here, because of the presence of these extra 2 terms, I cannot match order of h cubed terms in the Taylor expansion with the order of h cubed terms in my method. That is not possible. So, I can match the method that we are deriving, namely star, with the Taylor series method only up to order of h square term. That is, the maximum order possible here is a Taylor series method of order 2, namely terms up to order of h square in Taylor series can be matched with the method that I am looking for, namely star. So, the h cubed terms cannot be matched, and that will be the first neglected term in the Taylor expansion. So, I look at the equations which have helped us to match up to Taylor method of order 2. We observe that there are 4 constants C1, C2, alpha, beta, but there are only 3 equations. So, one of the constants can be arbitrarily chosen. So, let us choose, say, alpha to be equal to 1. So, let us choose alpha to be equal to 1, which will give you C2 to be equal to half, and therefore, beta will be equal to 1. So, when alpha is 1, beta 1, C2 half, and since C1 plus C2 is 1, this immediately gives you that C1 is also equal to half. So, we start with a choice, namely alpha equal to 1. This is one way of choosing. Any one of the constants can be arbitrarily chosen such that consistent solutions of this system can be obtained. So, this is the first case, namely the choice has been made like this. So, with this we obtain our method to be y0 plus C1, which is half, into K1 plus C2, which is again half, into K2, or it is y0 plus half of K1 plus K2. What are K1 and K2? We see that K1 is h into f of x0 y0, and what is K2? It is h into f of x0 plus alpha h. What is alpha? Alpha is 1. So, plus h, comma y0 plus beta K1. Beta is 1. So, plus K1. So, I have to evaluate the function where at the point x0 comma y0, and at the point, which is this point, x0 plus h, and the corresponding y argument is y0 plus K1, and I know what K1 is. But anyway, since this will be some number, K1 is some number which represents a slope of a certain line, right, and x0 plus h will be a number. What is this? x0 plus h is x1. So, when I start with the point x0, and move to x1, what am I doing? I am considering k1 to be h times the slope at x0 comma y0, and k2 which is h times the slope at the point x1 comma y0 plus k1. So, I have two slopes and I am taking the average of these slopes k1 and k2 and adding it to y0 to get the value of y1. It is a sort of an average of the slopes that is being taken, and the method that we have derived is this with k1 and k2 given by this, and we do not have any derivative evaluation of a function. We simply evaluate a function f. What is this function? The function f which appears on the right hand side of the given initial value problem at different points, namely one of them is at x0 y0, the other one is x1 at which we want the solution, comma y0 plus k1, and k1 is nothing but h f of x0 y0. So, we simply have to use this method and arrive at our solution at the point x1, and what we get is an approximation to the solution y of x1 at the point x1. So, we summarize and write down our Rungakutta method which we have derived. It is an explicit method, it is a single step method. So, it solves the initial value problem dy by dx is equal to f of x comma y subject to y of x naught equal to y naught, and when I require the solution say at the next point which is x naught plus h, then its solution is y naught plus half of k1 plus k2, where k1 is h into f of x naught y naught and k2 is h into f of x naught plus h comma y naught plus k1. So, this is my method, and what is the property of this method? This method matches with a Taylor series method of order 2, because up to h square term we have matched. So, it matches with Taylor series method of order 2. So, when you consider Taylor series method of order 2, what is the truncation error? It is of order h cubed. Since Rungakutta method matches with Taylor series method of order 2, we call this as Rungakutta method of order 2. Therefore, what is the truncation error? The truncation error is the order of the first neglected term, namely h cubed. So, the local truncation error of this method is going to be of order h cubed. So, we use Rungakutta method of order 2 to compute the solution at the first point x1. By taking the step size h to be small, the accuracy can be improved. Okay. What was our goal? Our goal was to go up to the point xn such that xn is x naught plus nh. We have just given the solution at x1. So, what do? And solve the initial value problem dy by dx is equal to f of x comma y subject to the condition y of x1 equal to y1. What is this y1? This y1 is what we have already computed. And so, what is the solution? Y of x2 is approximated by y2, and what is it? It is y1 plus half of k1 plus k2. And what are k1 and k2? K1 is h f of x1 y1 and k2 is h f of x1 plus h comma y1 plus k1. So, at every step you evaluate two functions. So, the method involves just two function evaluations and the method is of order 2. So, I can continue this and finally come to the solution at the point xn. So, to get this we again apply RK method of order 2 and get yn to be equal to yn minus 1 plus half of k1 plus k2. And what are k1 and k2? K1 is h into f of x n minus 1 y n minus 1, and K2 is h f of x n minus 1 plus h comma y n minus 1 plus K1. So, if you apply this, you obtain the solution at the point xn, or one can say that the solution of the initial value problem given by Rungakutta method of order 2 is this for values of n equal to 1, 2, 3, etc. up to n. So, when n is 1, y1 is y0 plus half k1 plus k2 with appropriate function values for k1, k2. When n is 2, you get y2 is y1 plus something, and continue this, you end up with a solution at the point yn. So, explicitly you determine the solution at each of the nodes into which you have divided the entire interval into n equal subintervals, and you go step by step to compute this solution. So, it is a single step explicit method of order 2 and is called Rungakutta method of order 2, matches with Taylor series method of order 2, and so it has a truncation error of order h cubed. So, we now move on to higher order Rungakutta methods, but before that we will see whether there are any other possibilities. So, the derivation is presented here. I thought it will be easier to follow when I discuss it on the board, and that is why we worked out the details on the board. But all these details are also available in the material that is displayed on the monitor. So, if you look at case 1, there we have chosen C2 to be equal to half, namely whatever that is given here has been considered and the RK method of order 2 has been obtained. It is also known as modified Euler's method, and I shall explain the details of why it is called a modified Euler's method later on when I complete the discussion on the Rungakutta methods. There is another possibility of solving the system of equations which we have written here, namely C1 plus C2 is 1, alpha C2 is half, and beta C2 is equal to half. So, let us look at the monitor and see what are the choices. I can also make C2 to be 1, in which case C1 will be 0, and alpha and beta will each be equal to half. Then in that case I end up with a method which is yn plus 1, namely y at xn plus 1 is yn plus h into f of xn plus alpha h, alpha is half. So, xn plus h by 2, then comma yn plus beta k1. So, h by 2 into f of xn yn. We call this as the midpoint method because we started with our initial condition at xn. We want to determine the solution at xn plus 1. We evaluate the function f at the midpoint which is xn plus h by 2. So, we call this as the midpoint method, and if you write down the truncation error in that method, which is the difference in the order of h cubed term that appears in our method star minus the order of h cubed terms which appear in the Taylor expansion, and that is what is presented as Tn in this material. The midpoint method that we have derived is again a Rungakutta method of order 2, because we have been able to match this method up to second order in Taylor expansion of the function, and therefore it is again a second order method. Now we move on to Rungakutta method of order 4. Now it is clear when I say I want to move on to Rungakutta method of order 4, it means that we would like to derive a method which involves 4 function evaluations, and the method must match with Taylor series expansion up to order of h to the power of 4. So, we write down this method which solves this initial value problem, dy by dx is equal to f of x comma y of x naught equal to y naught. My method is going to be yn plus 1 is equal to yn plus 1 by 6 k1 plus 2 k2 plus 2 k3 plus k4, where k1, k2, k3, k4 are function evaluations done at some intermediate points between xn and xn plus h. What is xn plus h? That is xn plus 1. What is xn plus h by 2? That is the midpoint of this interval xn to xn plus 1. So, function evaluations are done at points which lie between xn and xn plus 1, and it involves these 4 function evaluations k1, k2, k3, k4, and the method which is given here is a 4th order method such that it agrees with the Taylor series method of order h to the power of 4. Just one important observation, we need to solve for y in the interval x naught to xn plus 1. So, we divide the interval x naught to xn plus 1 into n plus 1 equal parts by means of points x naught, x1, x2, etc., xn, xn plus 1. So, any xi can be written as x naught plus ih, where I runs from 0 to n plus 1. That is why the solution is given here as yn plus 1 equal to yn plus 1 by 6 into sum of these 4 terms. So, we do not go into the details of the derivation of this method here. The method has to be derived similar to what we have done in the derivation for 2nd order method. So, write down the method, expand by Taylor series expansion for function of 2 variables. Now, you have to go up to order of h to the power of 5 for our method. Also, write down Taylor series method of order h power 5 and then match the terms up to order of h power 4 in Taylor series method and also in our method. Then you will end up with the coefficients which appear here to be 1 by 6, 2 by 6, 2 by 6 and 1 by 6, which we can call as C1, C2, C3, C4, and also the coefficients that may appear here as coefficient of h as half, coefficient of k1 to be half, here again coefficient of h to be half, k2 to be half, and here it is 1 and coefficient of k3 is 1. So, that the terms of Taylor series of order of method of order 4 agree with our method up to h to the power of 4 terms. So, we essentially have derived Rungakutta method of order 4. In particular, I would like to see what happens if the right hand side f of x comma y only depends on x, there is no dependence of f on y. Then in that case, what does this Rungakutta method of order 4 give? So, it is yn plus 1 equal to yn plus 1 by 6 k1 plus 2 k2 plus k2 k3 plus k4, but now k1 will be h into f of xn, k2 will be h into f of xn plus h by 2 comma yn plus what is k1? K1 is h into f, k1 by 2, which is this. What is this? F of xn plus h by 2 comma yn plus h by 2 f function of x comma y is simply a function of x alone. So, this is essentially h into f of xn plus h by 2. Similarly, k3 will be h into f of xn plus h by 2 and k4 will be h into f of xn plus h. So, we get yn plus 1 to be yn plus 1 by 6 k1, which is h f of xn, plus k2, which is 2 h f of xn plus h by 2, plus 2 k3, which is 2 h f of xn plus h by 2, and finally k4, which is h into f of xn plus h. So, you get yn plus 1 to be yn plus, I can remove this factor h from here. So, h by 6 f of x n plus 4 times f of x n plus h by 2 plus f of x n plus h. And do you recall what this method is? This is essentially Simpson's integration method. When we divide the interval x n to x n plus 1 into 2 equal subintervals when we want to apply Simpson's rule, then the Simpson's rule for integration between x n and x n plus h tell us that it is equal to h by 6 into sum of the end ordinates plus 4 times the intermediate ordinate, and that is what appears here. So, Rungakutta method of order 4 reduces to simply yn plus 1 equal to yn plus a term which comes from the integration of f of x comma y between x n and x n plus 1 by applying Simpson's 1/3 rule to that integral, and the error in this case will be of order of h to the power of 5. So, we shall conclude this discussion by taking a simple example of RK method of order 4 and applying it to say this equation. dy by dx is equal to x plus y, y of 0 is 1. So, I want to take h as 0.1 and would like to find out what is y at 0.2. So, I write down this method. I know f of x y is x plus y, x naught is 0, y naught is 1. So, substitute in the expression for k1, k2, k3, k4, the values are given here. Evaluate k1, k2, k3, k4 and then substitute in the method. So, you get y1 to be equal to 1.11034 and then start with the method and with the initial condition y at x1 is y1 given by 1.11034, obtain y2 namely y at 0.2, that will be y1 plus 1 by 6 into k1 plus 2 k2 plus 2 k3 plus k4. Again evaluate k1, k2, k3, k4 by substituting these values and you get y2 to be equal to 1.2428. So, the main computational effort in using RK methods lies in the evaluation of the functions f. So, the local truncation error in a second order method is of order of h square. The cost is just 2 function evaluations per step, and in the method of order 4 it is order of h to the power of 4. So, the table below shows you the number of evaluations per step that you require when you consider the order of local truncation error. This was given by John Butcher. So, you observe that in the second order evaluation of function per step, when you use a second order method, the best possible local truncation error is of order of h square. If it is 3, then truncation error is of order of h cubed and so on. But you observe that as the order of the method increases, say which lies between 5 or 7 or 8 or 9 or n greater than or equal to 10, the best possible truncation error that you obtain is only of order of h to the power of n minus 3. So, when n is equal to 10, you only end up with a method whose truncation error is of order of h to the power of 10 minus 3, namely h to the power of 7. So, the RK methods of order less than 5 with smaller step size are preferable to higher order RK methods using a larger step size. So, the values of the function y, which are solutions to this differential equation subject to initial condition by various methods are presented, namely Euler's method and then Rungakutta method of 4th order and modified Euler's method, which is nothing but Rungakutta method of order 2. They have been presented at a set of points, and the RK method of order 4 seems to be superior to the other two methods. So, in practical applications, one uses Rungakutta method of order 4 in solving initial value problems which are governed by the first order differential equations. So, we conclude this topic on Rungakutta methods, which are single step explicit methods, and in the next class we shall try to derive methods which are known as predictor corrector methods. Namely, there is an opportunity for us to predict the solution of an initial value problem, and this predicted value can be corrected and successively be corrected till the desired degree of accuracy is reached. So, we shall look into the details in the next class.